So today we're going to be covering the limit definition of the derivative, okay? So we've been working with limits so far, and we've probably covered this type of thing called average rate of change, abbreviated as AROC, because I'm not going to keep saying average rate of change. The average rate of change is a representation of what's called a secant line. Let me give you an example. Let's say I have a function here that is y equals x squared. All right, I didn't do too well on AP drawing, but you can tell this is a parabola. This is y equals x squared. So if I wanted to find the average rate of change between x equals 0 and x equals 2, I would find the slope of the line going through those 2 points. So I'd find change in y over change in x. So I would find f of 2 minus f of 0 over 2 minus 0. Okay? 2 squared is 4, 0 squared is 0, so this would become 4 minus 0 over 2 equals 2. So this 2, it's not my slope, because you can see that my slope is constantly changing. I don't have a line, I don't have a linear slope. Here at the bottom, my slope is flatter, then my slope is increasing and increasing and increasing and increasing. Okay? So if I were to draw 2 points, this would be x equals 0, this would be x equals 2, then the average slope of that line would be 2. So when I find the average rate of change, what I'm doing is I'm finding the slope of the secant line. The secant line is the straight line that connects both points. So the slope of this line right here is 2. The average rate of change of my graph is 2. So I can find the average rate of change of my function over an interval, but what happens as I take these 2 points and I keep moving them closer and closer and closer and closer together? Okay, I find the AROC over a smaller and smaller interval. Let's say I wanted to find how this function behaves as I move the 2 points closer and closer to x equals 0 right here. Okay, so I'm going to write f of x plus some added, some change in x, minus f of x divided by x plus delta x minus x. Okay? So what I have here is I'm defining one point as x. I'm going to say x equals 0 here. And my next point, I'm going to call it x plus something. Okay? In this case, it would be x plus 2. But I'm going to continually move this point closer and closer and closer to x equals 0. Okay? So 2 would be 0 plus 2. My delta x would be 2 there. And as I move my second point closer to 0, this delta x is going to get smaller. And you can see here in my denominator, I can simplify this and just have delta x in my denominator. I am going to try and find the tangent line. The tangent line is the line that touches the graph at only one point. Let me use another colored marker to distinguish this. I hope red shows up well on camera. I have it very thin. No, I can barely see that. Okay. Let me just draw a dotted line to represent the tangent line. Okay? It is the line that touches my graph at only a single point. So if I were to draw my secant line between these 2 points, you'd see that as I move the 2 points closer and closer together, the slope of the secant line becomes closer and closer to the tangent line. Means as these 2 points become closer and closer together, as they become almost the same point, they are going to converge to the tangent line. Okay? So we are going to express this as the limit as our difference in x goes to 0 of f of x plus delta x minus f of x all over delta x. Now this is how I like to write it. Some people teach it as the limit as x goes to a of f of x minus f of a all over x minus a, okay? That introduces two variables, twice the headache. Here, we're just dealing with one, okay? So as you can see here, if I try and do direct substitution, I get f of x minus f of x over 0. I get 0 over 0. I got an indeterminate form. But this is the formula for how we calculate the slope of the line at a single point. We calculate the average rate of change between 2 points when those 2 points are the same point, and that gives us the rate of change of our graph at a single point. This is what we call the derivative, the slope of the tangent line. So let's go through an example. Let's say I have y equals x squared, the same example we've been going through before. Let's take the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x, okay? So our f of x equals x squared. So let's plug in x plus delta x for x squared. That's going to be x plus delta x all squared. We have the limit as delta x goes to 0 of x plus delta x all squared minus x squared all over delta x. And we're doing the limit as delta x goes to 0. Okay? Let me FOIL this out. This is going to become the limit as delta x approaches 0 of x squared plus 2x delta x plus delta x squared. And we're going to remember this term, minus x squared all over our delta x, okay? Now we're going to be able to do some simplification. Our x squared and our negative x squared both cancel out. So now I'm going to be left with 2x delta x plus delta x squared all over delta x. So this is equal to the limit of delta x going to 0 of this term. Now let me try direct substitution. I plug in delta x equals 0, this term becomes 0, this term becomes 0, this time becomes 0. I got a 0 over 0 indeterminate form again. But what I can do here is I can factor out a delta x from the top and bottom. So delta x all times 2x plus delta x divided by delta x. And what I can do is I can cancel terms on top and bottom. I can use the replacement theorem, okay? I can remove this removable discontinuity, okay? And so now this is equal to the limit of delta x going to 0 of 2x plus delta x by the replacement theorem. By the replacement theorem. Now let's try direct substitution. And we get the limit of delta x going to 0 of 2x plus delta x equals 2x. So there we go. I found my derivative. Now if I wanted to find the derivative, or the slope of the tangent line at x equals 0, I would just plug in x equals 0 to this equation. And I'd get the slope of my line at x equals 0 is completely flat. It has slope 0. 2 times 0 equals 0. And there we go. That is the limit definition of the derivative. That's how you solve using the replacement theorem to find the derivative function for your original function. If you guys are able, only if you're able. If you think this deserves a like, please go do that. If you want extra help for anything science or math related, go to meekextrahelp.com or join our Discord server, both linked down below. Anyway, have a fantastic day and enjoy life.